Take it away.
Thank you. So welcome to the sessions entitled All You Wanted to Know About Collations, and whether it is all or you wanted to even more, or if this was far more than you wanted to know, well, we'll see. Anyway, I'd like to thank you to everyone who voted to have this session GroupBy. I'm very glad of that. This was a session I developed this year because I like collations. It's one of my favorite topics, but I figured maybe this will not be too popular by people who organize conferences and so on. So I'm very glad that I get the chance to present this one. Let's see. Yeah. So before we move on, I'd like to remind you that we have a GroupBy. We have a code of conduct here at GroupBy, and which simply means that if you ask questions in the chat or if you unmute, etc., you're supposed to behave nice and respectful. Don't say dirty things about anyone else, etc. So, because if you do, well, you will get kicked out. So anyway, my name is Erland Sommarskog. I live in Stockholm, where I work as an independent consultant. I've been an MVP for many years, and I have my website, sommarskog.se, which you can say, well, a small collection of large articles. However, there is no articles on collations there yet. Maybe I will write one. Here's my email address. So if you have any questions that I don't answer right now, you're more than welcome to get in touch with me. I also like to point out that slides and scripts for this presentation is available on my website right now. So must go to se/present. There you have a list of all my presentations. And if you wonder about this picture here to the left, well, that's a Swedish summer forest, and then you have to figure out the rest yourself. Also, we have sponsors. Very glad to I like to give big thanks to these, because I have a suspicion that without these sponsors, we would not be doing this event. So big thanks to these: Redgate, Solomons, Straight Path, Solomons again, yes, Pure Storage, and Dallas DBA. So here's my agenda. I will start to talk about collation basics. So, well, what is a collation and where we can define it in SQL Server. I will then divert a little bit and talk about Unicode and code pages, because that is something which is affected by, or well, involved with collations. I will then go and pick apart the autonomy of a collation name, all these CIAS, what all this stands for, and that will be quite a big part of the presentation. And they will eventually lead us to discussion about the UTF-8 collations that were added with SQL 2019. I will then talk about two pain points, you could say, with collations, for pain points for two different reasons. The first one is metadata, and the other one is conflicts. I will show you some useful tricks with collations where you maybe didn't even think of using collations. And finally, I will talk a little bit how collations can affect performance. So what is a collation then? Well, a collation, that is a set of rules for how to handle string data depending on human language. I mean, because people speak different languages and expect data to be handled according to their language. So for example, comparing data, is this one an uppercase I without any dot equal to a lowercase I with a dot? Is single v equal to w? Is this one, or no, with the dots over, or as I would call it, greater than z, or maybe smaller? Is plus, does it come before or after minus? Now, you might think that any of these are right, it's always the same, this can never change. Beware, you will see examples how all of these four will be different during this session. Now, once we have the rules for sorting, that also defines grouping, once we have the rules for comparison, that also defines the rules for grouping and sorting, because if these two are equal, well, they will group together in the GroupBy. If they were unequal, they will be in different groups. And same thing for sorting. If this one is greater than this one, well, then it will sort after Z, else it will sort before Z. The rules for upper and lower are also affected by a collation. Yes, not all languages have the same rules. You will see an example of this. Like ranges is also affected by collations. This is something that sometimes bites people. And we'll come back to that towards the end. A collation also controls which code points in Unicode that actually are available and that are defined. This may not register right away, but don't worry, I will talk more about that later. And also, the collation controls which code page to use for varchar. That is, which characters are available when we use the varchar data type. And here's an interesting tidbit. Not all collations support the varchar data type. You will see one example of this. Now, in SQL Server, we can define the collation no less on 4 different levels. And the first one is the server collation, and which we set when we install SQL Server. This one controls the collation for the system databases, and it is the default collation for string columns in temp tables. And the server collations also serves as a default for the database collation. But when we create a database, we can say, no, I don't want the server collation. I want that collation over there in the right corner. And then the database collation, well, that sets the collation for string variables and the literals. And it's also set to default collation in user tables and table variables in difference to temp tables. Then when you create a table, you can say, no, for that column, I want that collation on the on the third shelf from the top. Please give me that one. And finally, you can, when you have an expression, you can cast the collation on the fly. In this session, I will use these three quite a bit more than once. You will not see me installing SQL Server. That would take too much time. But there's one thing, though, I like to call out when it comes to the server collation, and that is when you run it up and you come to this page, the server configuration. You have the collation. It's tucked away here on a secondary tab, so it's not splashed in your face. But always make it a habit to look what you have there, because it may not be what you expect. The default in the setup wizard is taken from the Windows system locale, and that may be different from your personal regional settings. And even if the Windows system locale is the same as your regional settings, well, the collation may still not be possible. Oh, sorry, may still not be the apt one for your language. So if you have a Polish system collation, no worry, you will get a Polish system locale, you will get suggested a Polish collation. If you have a Norwegian system locale, no, you will not get a Norwegian collation. So it's always a good idea to check what you have there, because changing the collation after the fact, it's a pain. Here is more for a reference. So if you want to find out what is the server collation, you can use this function server property. Or if you use the database collation, you can use the database property X, give the database name and collation, or you can look at sys databases for both of them, because the system databases you will see those there. And for the column, you can simply do SP help on the table, and that will be the rightmost column in the second result set, or you can look at the sys.columns. So let's now talk about Unicode. This is a character set. Well, the Windows is based on Unicode. All modern operating system, all modern computing is based on Unicode, which is a character set that supports all human languages. And in total, it's possible in Unicode to define 1.1 million code points. That takes up 21 bits. Today, there is as many as 143,000 defined, which is kind of a scary number. Anyway, and every once in a while, they come up with new versions of Unicode to define more and more code points. And the collation SQL Server is tied to a certain version of Unicode, and what the impact of that, I'm going to talk more about that later on. Now, one thing you should know is that all living languages, they can be expressed with a so-called base plane. That is the code points from 0 to 65,535. That is the lower 16 bits. Also good to know is that the code points from 32 to 126, that is the ASCII we have known and loved with computers since way back in at least the 70s. And also the code points from 160 to 255 is the fairly common standard Iso-Latin 1, which is good for Western Europe, and which has been around since, well, the mid-80s. And here are some sample code points from Unicode. And you always, in Unicode, the convention is to write them as U plus and the code in hex. So it's A, capital A is O plus 0041, which you may recognize also as 65 as an ASCII code. Here you have a Polish character, here's a Greek character, here's a Japanese character, and here's a playing card, which is one of these characters beyond the base plane. And it's only when the character is beyond the base plane we use more than 4 hex digits to denote the character. Now, we can encode Unicode in more than one way, because these are only the code points. When we put them in the computer, we can do that in different ways. So one encoding is UTF-32, and this is very simple-minded encoding. There's 4 bytes per every code point, but it takes up space, and it's not very commonly used. Very popular in the Western world is UTF-8, which is used as it's variable length encoding, so there is 1 to 4 bytes per code point, and we'll get to see more details about that later on. And it's also commonly used. I think Linux, for example, uses UTF-8. Many systems use UTF-8. However, not Windows. Windows uses UTF-16, which has 2 bytes per every code point in the base plane, and then 4 bytes per code point for the rest. And we will also see how that works later on. And as I said, Windows is based on UTF-16, and from that follows in SQL Server, the data type envarchar is UTF-16. Now, we have not always had Unicodes. There were computers before Unicode, and before that we have smaller character sets, and Windows supports these, and the terms in Windows is code pages. And all these code pages in Windows, as far as I know, have ASCII in the range from 32 to 126, and then the range from 127 up to 255 is used to support 1 or more languages, but far from all languages. So each of these code pages is targeted for a certain group of languages. So for example, CP8H50 is for Western Europe, and this code page was originally designed for MS-DOS and it's just proprietary from Microsoft and is not interoperable with other systems, because way back in the 80s, about every vendor had their own 8-bit character set. Code page 932 is for Japanese, and then we have 1250 and 1252, which both are drawn from the 8-bit standard ISO 8859. So 1252 is Latin 1 for Western Europe, Latin 2 for Eastern Europe. And then there's also code page 65001, UTF-8, because as far as Windows is concerned, UTF-8 is just another multi-byte character set. Yes, that is the terminology. And you might think 8-bit, multi-byte. Yeah, well, we're going to see that just in a second. So anyway, these code pages, they are the foundation for the varchar data type in SQL Server. So let's have a look at this. So first of all, we're going to look at the server property, at the server collation for my instance, so you know where I am, and also the code page for that one. So you use collation. You can use the function collation property, give it a collation name, and I need to use converter because this one returns SQL variant, and then the property code page. So we can see this. And I have the collation Finnish Swedish 100 CSAS. Well, I'm Swedish, so that's why I have a Swedish collation. And the code page is 1252 for Western Europe. So now here I got to select 3 words, all the same 3 words in 2 different ways. Here there is an n in front of the literal, which means that the data type of the literal is nvarchar. Here there is no n, so the data type is varchar, which means that not all characters are available. So there are 3 words, and we're going to look at these. So this word, räksmörgås, it's a Swedish word meaning shrimp sandwich, and I like this word because it includes all the 3 characters in the Swedish alphabet that are not in ASCII. And you can see also in varchar we get back as it was originally because I got a Swedish code page. Here I got a Polish word, słońce, which means sun. But here, if you look closely, you can see that there is a slash on the L and there is an accent on the N, which is missing down here because these 2 characters are not available in 1252. So they are being replaced with 4-byte characters, which means characters that look similar, basically the original character without the extra diacritical mark. And here we have a Japanese word or a name, Nakameguro, that's a district in Tokyo, but there is nothing like that looks similar. So we get the generic 4-byte character, the question mark, 3 of them. Now let's move over to a database called Japanese CIAS. All databases I'm going to work with today will have the name of a collation and use that collation. So you can see here, I'm saying create database, collate. I want that collation for this database. And we're also going to look at the code page. And now it's 932, Japanese code page. I'm going to look at these 3 words again. And now you may see that räksmörgås now comes back as raksmorgas. Well, if you don't know Swedish, you might think, hey, that's the same. What's the difference? Hey, I'm Swedish. I know the difference. This means, well, nothing. But anyway, because these characters are not available in Japanese, so they get replaced with similar ones. For some reason here, the Polish characters get replaced with question marks, but now Nakameguro comes back as Nakameguro also in varchar. Now let's have a look at some more of this, because give this a thought. So if you think that these are just a 8-bit character set. Now remember, these are ideographic characters. This character here means middle. It has a translation directly into English. So do you think that only 127 of those? No, of course, there's about thousands of them. So how do they do that? Well, I'm going to put this into a table, Nakameguro and also Yokohama in ASCII, and I'm going to look at the length of the word in characters. That's what the length function, it returns the number of characters, excluding trailing spaces, and data length, which returns the number of bytes. So, and it's a varchar 8. And we can see here, this one is 3 characters, but it's 6 bytes, whereas Yokohama here is 8 characters and 8 bytes, because that's the ASCII part of the code page, but this is the Japanese part of the code page. And what they do is that they take 2 bytes. So you have to combine 2 bytes to get one of these characters. So it's not 255 characters only. Now, this is varchar 8. So we have another Japanese word, or well, the name, it's a railway station in Tokyo. That's 1, 2, 3, 4, 5 characters. So it should fit, shouldn't it? Or no, we get string of binary data would be truncated in table and create a value as, and you can see the last character is missing. Because varchar 8 does not mean 8 characters, it means 8 bytes. Yeah, that's the way it is. And well, the Japanese people have had to put up with this since SQL 2000 was introduced. Oh, sorry, since SQL 2000 introduced Japanese collations. One more thing we're going to look at while I'm at it is I'm going to create this table called India. And here I'm going to force the collation of this column to be Indic general 90 CIAS, and the data type is nvarchar. And that worked well. Now we're going to create a table called India 2, and I'm going to have the same collation, but now a varchar column. But I get an error message. Collation Indic general 90 CIAS is supported on Unicode data types only and cannot be applied to char, varchar, and text data types. So this is one of these collations that do not support varchar, and we can just see here that I got the same error message if I try to create a database with that collation, because it's kind of still have a default collation that I can't use for varchar. So what is the code page for this collation? Well, it's 0. There's none at all. And why there is not a code page for Indic languages, I mean, after all, there are quite a few people in India, I don't know, but maybe they never come around to do one. But there are a couple of collations that do not have a code page and can only be used for nvarchar. Quite a few are like not only Indic, I think the Bengali, Assamese, the Nepali collations are like that. Of the European collations, I think Maltese is the only one, if memory serves. So, yes, varchar is not always 8-bit. That's a good thing to know. Let's talk about all the collations that are on SQL Server and what there are. There are no less than 5,508, or actually, that's 5,681, including also the deprecated ones. That's quite a lot. And they fall into two groups. And the main group is the Windows collations, which there are 5,431, or 5,603 if you include the deprecated ones. They are based on the Windows system locales. The documentation says exactly what that means. I haven't really figured out, but I guess it means that, well, if we have, let's say, Nepali collation, well, then SQL Server is going to work with Nepali data like Windows would work with Nepali data, more or less. Although not necessarily like in File Explorer, because Windows Explorer is doing some kind of smart sorting that would not be good to do it with large amounts of data. What is important to know about Windows collation is that even if you work with varchar, all operations are carried out in UTF-16, so they will do conversion to UTF-16 and possibly back if needed to do the operations. Then we also have the smaller group, the SQL Collisions. These are legacy, way up to SQL 7. SQL Server in a single instance, you could only have one single collation, or rather sort order as the terminology was. And that was applied to the entire instance. You could not set one on server, one on database, one on column, one on expression level. It was one size fits all, do this. And for these SQL collations, the varchar has no relation to UTF-16. It's based on a specific code page with that own library. Basically, that goes back to even earlier days in SQL 6.5 and earlier, when SQL Server did not support Unicode at all. There was no nvarchar data type. But for nvarchar, well, the SQL collations work like a Windows collation. Although these are legacies, so should stay away with them, you should never use them. Well, the most commonly used collation in this world is this one, SQL Latin 1 General SQL1 CIAS, because this is the default collation if you install SQL Server with a system locale of English United States. Is the default collation on Linux and Docker, where you have to always specify it on the command line when you install. It's also the default for anything you do in Azure. As a matter of fact, if you install an Azure VM for SQL Server, you cannot even choose the collation and install them. You have to change that afterwards. But I will mainly talk about the Windows collations, but I will show some funny things about this one as well. Now, we have a collation name here, Polish 100 CI, AI, KS, WS, SC, UTF-8. What does all this mean? So here's a quick summary. So Polish, that is the collation family. 100, that's a version number. Well, CI and AI, that's about case and access sensitivity. KS, WS, VSS, right now, I'm not going to say Japanese. I'm going to talk more about that later. SC stands for surrogate compatible. That can also be bin and bin2 for binary collations. And finally, we have UTF-8 for UTF-8 support. So we're going to take this now more one by one. Let's start with the collation family. So a collation family can be for a single language like Polish or Assamese, for example. Some languages have more than one collation family. So there's traditional Spanish and modern Spanish. Why? You will learn a little bit later. Some languages share a collation family, like Finnish and Swedish. We have the same rules. Could be because Finland was part of Sweden for quite a long time. And then we have Latin 1 General, which is a bigger family for languages that uses the Latin alphabet and have common rules in common. Not extremely a lot of languages, but quite a few widely spoken ones like English, German, Portuguese, Italian, and Indonesian. Even, well, Dutch is not really that widely spoken, but hi, it's one of these. They will also have a Cyrillic General for languages that use the Cyrillic alphabet, mainly Russian, but there's also Bulgarian, Belarusian, and not Ukrainian, they have their own collation, but also quite a few languages spoken in Russia, like Moldovan, Chuvas, etc. And the collation family determines, well, for the basic, first of all, the basic sorting and comparison rules, because of course they come from the alphabet of the language and what rules the language have. But then they are further refined by whether it's case or accent and sensitive, etc. And also the version number can have a minor impact. You will see one example of that later on. And also the rules for upper and lower, because that comes by the language. And the code page for varchar, with the exception for UTF-8 collations. Now we're going to have a look at some collations families, and this demo is more for fun, just to show you how different languages do things differently. Before we go there, though, I just like to show you this function, sys.fn_help collations, that lists all the collations that are on SQL Server. So here first the Albanian ones, here's the Arabic ones, etc. And we can see down here that yes, the number is, oops, 5,500 up. Well, okay, sorry about that. 5,508. So anyway, I'm going to create a database here called lat1 general, CIAS, and move over to that one. I'm going to create a table called sort words, and which has a number and a word and a remark. And the purpose of remark is that if you wonder what any of these words mean, you can read the remark column. I'm not going to spell that out. I'm going to add a couple of languages, and the number here will be according to what you will get in English or in Portuguese or Italian that uses lat1 general. So we can run this as from the beginning, as without any, or running with the collation of the database, and you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and you can see here that this A will ring over sorts after A1, but this one A with the tilde over sorts before that. Well, that is because this accent, as we can call it, because this ring doesn't mean anything for English, so the English thinks, oh yes, it's just like an A. But it's because that accent only matters if nothing else differs. So this one comes after this one simply because else comes after A, and this one comes before. Nyandu comes before Netherlands because A comes before E. Now, anyway, let's now force the collation when I sort to be traditional Spanish. This is what I do. I say collate, word, collate, traditional Spanish. And now I get 1, 2, 3, 5, 6, 4, 8, 7. So, and 9, 10, 11, 12. So Chicos moved to be between Center and Chardas to be right before Netherlands. This is because in the Spanish language, up to 1994, CH was considered a separate letter and had a separate entry in the dictionary. Then in 1994, the Royal Spanish Academy said, no, wait, this is too difficult for the computer age. Now, the computer will never be able to sort this out. So they decided that CH and LL would now sort, so CH will sort between CJ and CK, and LL will also sort right in L. So LL was also considered a separate letter. And so this is traditional Spanish. Modern Spanish would put Chicos up here, or also up here. Still though, Nyandu, because N with the tilde over is still considered a separate letter in the Spanish language, so it's a separate pronunciation, and therefore, and it sorts between N and O. Now, let's try Hungarian and see what we get now. 1, 2, 3, 4, 6, 7, and 10 and 9. So Chicos is back in place, but now Chardas is between cycle and Nyandu, because in Hungarian, CS, which is pronounced just like CH in Spanish, counts as a separate letter. Still, they haven't changed that. It counts as a separate letter and comes in the dictionary between C and D. Or yeah, unless I forgot some other letter. And also, they have O with dots over O, which in Hungarian also counts as a separate letter, and which they saw has a separate entry between O and P. So that's why these two change places. Now, let's go to Finnish Swedish and see what happens now. 1, 3, 4, 6, etc. 10, 8, 10. Oh, 2, 9 at the end. So Swedish has, as you might recall from the first demo, 3 extra letters that are not in ASCII, and you see 2 of them here: A with ring over and O with dots over, or O and as we would say, and this is the third to last letter in our alphabet, and this is the last one. Yes, because in difference to Spanish and Hungarian, we did not place them right after the similarly looking characters. Now we decided to put them at the end of our alphabet. So that's why you have them down here. And then we're going to move over to our neighbors, our Swedish neighbors, Danish and Greenlandic. Well, these roots probably come mainly from Danish. And now it starts on 3, 4, and we have 9, 2, 1 at the end. So Danish also has 3 extra letters with about the same pronunciation as the Swedish ones, but they look differently. So they don't actually have O with dots over, they have O with slash. But it's pronounced the same way, and therefore they consider O with dots over to be, oh, well, kind of an accent of the O with slash. But why have these changed places? Well, in Swedish, we introduced this character in the end, towards somewhere in the 15th century, I think. In Danish, they added this one not until 1948. Yeah, they're a bit behind. So before that, they used to spell this sound as a double A, and they still do in some proper names. So that's why double A co-sorts with a ring in a Danish collation. And you get them here. So let's then move over to the version number. And the version number can be none at all, which we then can say stands for 80. And those are the original collations that were introduced in SQL 2000. Then in SQL 2005, they added support for a few more languages. And then in SQL 2008, they added support for even more languages. And also they supplied new versions of the original collations from SQL 2008. And in some cases, they also changed name, etc. Then, well, they added also new collations in SQL 2012, but they had no version of it because they were only new features. But then in SQL 2017, they introduced collation with a version number 140, but these are only for Japanese. Now, it's not so much here the version number for SQL Server that is of interest. What is of interest is that each of these ties to a certain version of Unicode, although I've not been able to find the mapping. But this in its turn defines which code points that are defined. Now, that may not ring a bell. What does this mean, you might think? So let's show you. I'm going to show this. I'm going to move to my database, Latin 1 General CIAS, and I'm going to declare a variable here called sun with the value of swanso, which is Polish for sun. However, if you've been paying attention, or if you know Polish, oops, that was the wrong one. If you've been paying attention, you will see that this word is misspelled because this is an N with a grave accent, but Polish does not have this character. They have an N with an acute accent. So anyway, I'm going to look at the uppercase of this version. I'm going to try to replace the bad character with the correct one. I'm also going to try to find it with character index, and I'm going to try to compare it to Swatse without any N at all. And the outcome of all this is not what you might expect. This one is still a lowercase, and it's still a grave accent. And car index does not find the character, and it's equal. What? This sounds crazy. Well, now let's move to a database called Latin 1 General 100 CIAS. So we're going to move to a newer version of Unicode. And now we're going to do the same exercise. And now we get it all uppercase. Replace, does it work? We now have a correct spelling of it. Car index finds it, and now it's not equal to Swatse. So this is the story. Way back in this version of Unicode, they have not yet defined this code point, U plus 01 F9. It was just the proper representation in a font that would be based on this version of Unicode would just be an empty square, or sorry, empty rectangle. But SSMS uses a much newer, uses a font which is based on a lot newer version of Unicode. So, and SSMS does not understand what's coming back, what SQL Server thinks about it. So that's why it's kind of confusing. But for SQL Server, this means nothing. So up, of course, since there is no, it is not a letter, nothing happens with upper, and replacing car index says, oh, this is an undefined code point. I don't know what to do with this. I do nothing. And same thing here, because it doesn't mean anything. Well, it is equal to Swatse because it's just white noise. But here it's being handled properly. And if you wonder where this character is used, I've seen it used in Pinyin and wait-write Chinese with Latin letters. Now we're going to look at a character table called sortcast. Also one thing here about collation and version numbers. So in this one, I got a number, I got a CH column and NCH column for car1 and NCar1 column. And I'm going to add the same characters to both of these columns. So we're first going to sort this according to the database collations, which is a version 100 collation by the car column. And you can see I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's the number reflects the original sorting. And if I switch this to be ncar, I get the same sorting. I always do that. I would always get the same result with a Windows collation, no matter whether I use varchar or nvarchar for the same characters. Because, as I said, all operations for varchar are actually performed in UTF-16. Now I'm going to try this collation instead, a Lat 1 General CIS, so it's version 80 and an older version of Unicode. And now for some reason, I don't know why, but you see 1, 2, 3, 5, 4. This euro character now sorts in a different place than it did before. Not exactly why, but for some reason they found it apt to change that. Now we can also look at this collation here, SQL Lat 1, CP1 CIAS. And this is the NSH column. This is the one we sort by. So we get the same result. I don't know for sure, but I suspect that these, for nvarchar or ncar, these two collations are perfectly equivalent, but I don't know for sure. But if I sort by scar now, and remember this one has a separate library for varchar and car. 1, 5, 2, 3, 4, 8, 9, 6, 7, 10. So the plus character now comes before the minus, and these two letters, S hatcheck, uppercase and lowercase, now comes before the digit. Why? Well, I don't know. One theory that I have is that originally in this code page, there were different characters here, some punctuation characters, because these, although this is Latin 1, these are in a part of Latin 1 which is actually not defined. So these are extensions that Microsoft added to 1252. So they are not with the standard of Latin 1. So let's now talk about case, case and access insensitivity. So, well, this is quite simple. CI stands for case insensitive, and then insert in all lowercase is equal to insert in all uppercase. And if it's case sensitive, well, then they're different. Then we have accent insensitivity. So if it's accent insensitive, these two English words, resume and resume, are be considered the same, which is quite fortunate maybe for the English people, because, you know, English people can't spell their own language. They basically have, even though the resume is supposed to spell this, being spelled this way, they don't do that. At least the ones, the left ponders are, well, yeah. I'm not sure not to offend anyone, so let's skip that. Anyway, if they are accent insensitive, they are being considered being different. So let's have a look at this and what some interesting impacts of this. So first of all, we're going to move to this database, Latin 1 General 100 CIAS, and yes, they are being equal, no surprise there. And now we're going to create a database called Latin 1 100 CSAS, so it's case sensitive, and they're being different. Now, while we're at it, let's have a look at how case sensitive sorting works, because this is something that sometimes surprises people. So I'm going to create this table called case sorting, and there is a number column, and there's word and the data. So, and I'm going to sort by both word and data. So, in case the word doesn't sort, or in case the words are not considered the same, the data will sort of the data. So first going to do this sort this data according to Latin 1 General CIAS. And then we can see what I get the order that I have with the numbering. So Andrew, asserting Australia, nothing surprising that, of course, I got uppercase and lowercase mixed. And then I got mixed plus case, mixed case, and mixed case. Well, in various sort of weird combinations of uppercase and lowercase, no particular pattern. But of course, it's case insensitive. And we can see here, though, that 6, 3, 37, 8. So it's sorted by the data column. But mixed plus case, here the plus is considered a separate letter. Now why does mixed underscore case come here at the end? Oh, we're going to talk about that later on. Now let's change this to Latin 1 General CSAS and see what result we get. First of all, these three words are still sorted in the same order. Andrew asserting Australia. It doesn't matter here that A is considered to be different from lowercase a is considered to be different from uppercase a, because case sensitive sorting is the case will only matter when nothing else differs. So, and of course, this is how we want to find things in the dictionary. We don't want to, oh, here are the lowercase words, and I want to find, okay, the uppercase words, I would have a separate entry for them. No, that's not what you want. And we can see here now that mixed case, now there's sort of logic here. Mixed plus case first comes first, but then we have mixed case all lowercase, then mixed case with only capital M, then with both capital M and C, and then mixed case at the end, all uppercase. And mixed case comes here. So in a case-sensitive collation, a Windows case-sensitive collation, lowercase sorts before uppercase. And a hyphen, the hyphen also only has a secondary weight when sorting. And this is also how we want to find things in the dictionary, because some words are being spelled with a hyphen, but we may not know. So it's more easy if we just ignore that, and if nothing else differs. Whereas on the plus, on the other hand, is normally used in part of the word. So that's why the plus is just considered like any other letters, and then plus sorts before C. And finally, let's try the collation SQL Lat1 General CP1 CSAS. So this is an SQL collation, and this is a varchar column, remember, and you can see they do it differently. These are the same, but now here, mixed case and all uppercase comes first. So in SQL collations, they think that an uppercase should come first. And this is just a convention. I think the reason lowercase comes first in Windows collation is that there's some general, not part of Unicode, but some convention tied to Unicode that says lowercase comes first. And also SQL collations does not have any particular handling of the hyphen, so they will sort that before D. Or sorry, sort that before C. Now let's see. We're going to try this collation. We're going to move, says SQL Lat1 General CP1 CAAS, and because this one has more fun with one character, I'm going to look at the word Košice, which is a city in Slovakia, and I'm going to compare Košice to in all uppercase, in almost all uppercase, but this one lowercase, and then the same thing for nvarchar. And here is a weird thing, because this one is not equal. Although this collation is case insensitive, it's not case insensitive for this particular letter. But as I speculated, this might have been thrown in later. So originally, maybe this was something else in this collation or sort order. Now let's have some even more fun. We're going to create a database called Turkish CIAS with that collation. And then we're going to compare insert to insert. So what do you expect now? Different. What? Yeah. So let's have a look at the upper and lower of these to see what's going on. And look here. There is a dot over the I. And look here, there is no dot over the I. You see, Turkish have two I letters, the dotted I and the dotless I. And that might seem like, why do they do something like that? That's stupid. Well, hey, this was designed in the early 1900s when there was, well, basically only Ada Lovelace knew what a computer was. So no one cared about that. From a phonological perspective, it makes perfect sense, but I'm not going to go into those details. Anyway, so here I have Istanbul, properly written in Turkish. Should be a dotted I compared with a leading uppercase and to all uppercase. And I got the word Kizil, which means red, in lowercase and uppercase. And it's Turkish, insensitive, and yes, they are equal because they are versions, uppercase and lowercase, of the same letter. Now, if I go back to my Lat1 General 100 CIS, they are not equal because it's case insensitive and it's accent sensitive. And these are now different letters, but different accents on them, so to speak. But now I'm going to move to a database with a case insensitive and accent insensitive, a Finnish Swedish one. Sorry, I'm going to need some water, I think. And again, I'm going to compare these, and they are equal. And so, because now it's accent insensitive. And we're going to have some more interesting observations about accent insensitive. So I'm going to create this table with a left word and a right word, and a column English, where I'm just going to say, compare the words according to the rules of English. I'm going to cast the collation to Lat1 General CIAI. I'm going to do the same thing for Polish, using a Polish collation. And for Swedish, I don't need to force the collation because I already have the Swedish collation. And now we're going to add some words, and we're going to look at the outcome. So the first pair is a resume and resume, and they are considered being equal in all three languages. So at least English and Swedish uses this character. I'm not sure about Polish, but it's not considered a separate letter. It's just in Swedish, for example, it's used to mark stress in some words. So it's considered, it is just an accent. Then we have słońce. It's a Polish word, and here's slonce, which has maybe the English or Swedish people will write it because an English or a Swedish person doesn't understand this slash and this N. It's just some flea crap. So yeah, so they are the same. So English and Swedish think they're equal, but Polish does not because they are separate letters in the Polish alphabet. And here we have the English word cooperate being spelled in two different ways. This is the most common spelling. Some people spell it with a hyphen, and some people, not very common, but some do it, put DRSs on the top of the second O to mark that it's cooperate and not cooperate. And English and Polish rightly thinks that they're equal, but in Swedish, no, they are not equal because, well, this is our last letter in our alphabet. We think cooperate, but in this case, it's not mark and umlaut, it's just help the pronunciation. And then we have another two different English words, wine and vine. And of course, English thinks they're not equal. Also Polish, although Polish does not use the V character. But hey, in Swedish, yes, they're equal. Because in Swedish, the W is just some sort of, well, accented V. We pronounce, well, it's just spelling variation. We pronounce it the same thing. You know, the English people, they go on saying WWW. We simply say VVV. as it had been spelled, VVV. So yes, this is not a separate letter in our alphabet. Oh, well, at least it wasn't when these collation was defined. And finally here, this one is also kind of funny. You might, how can these two be similar? This is U with dots over and a Y, but they are considered to be in accent insensitive collation the same in Swedish. But this character here is known in Swedish as a German Y. They're being pronounced the same. So let's see. I'm going to check how on my time. Well, let's see. No, I'm probably behind. Let's see. Anyway. So this is just a summary of what I talked about. In the case-sensitive collation, case only has a secondary weight when sorting. Case-insensitive, watch out for turkeys, and accent-insensitive comes with surprises. The more languages you try, you can find more interesting things like that, things you might not expect. So let's not talk about the Japanese matters, the KS, WS, and VSS. So in Japanese, they have, previously we saw Nakamiguro written in kanji, but Japanese also has two syllable scripts, hiragana and katakana. And here we have Naguro written here to the left in hiragana and here to the right in katakana. You probably would never write it in katakana because basically I think katakana is used for foreign words. Anyway, are they the two the same or not? Well, as long as the collation name does not include KS, it's kana insensitive. But if it says KS, they are being considered different. And then we have WS. This is maybe a little bit more weird, but when you write text in these languages, you may note here that these characters are actually quite a bit wider than the Latin letters. So what they do is they like to render Latin letters in wider, so they match up in space with the hiragana, katakana, or the ideographic characters. And they've also coded that into their character sets, and that has also made its way into Unicode. So here to the left, we have Paris in half width or normal width, and here we have it in full width. And also for katakana, there are also half-width versions of katakana because maybe you have a text which is mainly Latin, then they want to throw in some katakana, I don't know. Anyway, are these equal? Yes, they are equal as long as the collation name does not include WS for width sensitive. But then they're and if WS, they are considered different. Finally, VSS stands for variation selectors and sensitivity. I will have to pass on this one. I've not been able to figure this out very closely. It's not really only for Japanese, but probably most important for Japanese because the only collations to have VSS are the Japanese collations with a version number 140.
I'm disappointed. I thought you knew this stuff.
Yeah, well, I know something what variation selectors are about, but not enough to do it in a demo. And I was not able to figure out whether actually this made a difference. So I will need to read up more on Japanese to figure this out. Let's talk about binary collations. So they sort of compare by the code point. They are case, accent, kana, everything else sensitive, which means that they may not be that user-friendly, but they are fast. But to confuse matters, there's two of them, bin and bin2. Why? Well, let's have a look at this, and I need to show a demo to demonstrate this. So we're going to move to my database, and I'm going to create a table called binary test, and I'm going to enter three character combinations, DE, DN accent, and L/N accent, or N, if I want to do that in Polish. So then we're going to look at the code points, both in decimal and in hex. And we can see here, they're sorted in this order by code point 68, 69, 321, 323, and 0044, 0045, 0141, and 0143 in binary. Now, I might think, okay, why do I need binary representation? Can't I just cast a binary and sort them that way? Let's try that. And we get them back as L/ comes before the D and N accent comes before the E, which, well, okay, when we look at the binary representation, of course, that makes sense because it's 4101 comes before 4400. But why are the bytes swapped? Well, that has nothing to do with the collations. That has to do with how computers are built. The Wintel platform is a so-called little endian platform, which means that when you address a word, you will get the bytes swapped. That is just the way things are. So then if you have Latin 1 general bin 2, you get things in the order we expect, because when you sort by this collation, they do swap all the bytes, all the words, so you get the bytes in the right order, and you get them by code point. So what then is a bin collation? Well, let's see if we can figure this one out. Well, the D comes before the L/, but the N accent comes before the E. So what they do is this. They do swap the bytes of the first word, and the rest they swap on the raw binary. And please don't ask me what they were thinking when they came up with this idea. Maybe they thought it would be faster, but I've not been able to find any differences. Anyway, the bin2 collations are newer. They were introduced, I think, in ISCO 2005, and these are older. And they are legacy collations, I would say. So That's why you have this. Let's now move over to SC, well, where the documentation says supplementary characters. I tend to read this as surrogate compatible. In UTF-16, so I told you, characters beyond the base plane, they are encoded in, you need 4 bytes. And the way it's done is that they're encoded in so-called surrogate pairs. That is just the name, surrogate pairs. Don't ask me why it's called that way. So the high word will then be in the range from U plus D800 to U plus DBBBB. And the low word will be in the range from U plus DC00 to U plus DFFFF. And then Unicode does not define any characters on these code points. So Unicode is designed with UTF-16 in mind. The original collations that were added up to 2008, they only supported the Unicode base plane from 0 to 65,535. Then in SQL 2012, they added SE collations that support UTF-16 in full, and they added SE collations for all collations with the version 80 and later. Version 90 and later, not the version 80 collations. So, and if you look at the version 140 collations, you will not see SC in the name because they are by definition always surrogate compatible. And binary collations, on the other hand, are not really surrogate aware. So, going to move to my database Latin 1 General 100 CSAS, which that is not surrogate aware. And I got this variable here called Gothic, where I got to assign, well, 5 letters from the ancient and historic Gothic alphabet. No one speaks Gothic these days. The language is extinct, and also thrown in an emoji. And then I'm going to look at the length of the word in characters, the length in bytes, and I'm going to look at the use substring to extract the first 3 characters from that word. And you can see I get back the word correctly, but SQL Server says no, there are 12 characters in this word, which is kind of wrong. And the first 3, well, we can see we get the first one, which is kind of an A, but then we get this square with a question mark in it. This glyph means encoding error because Management Studio thinks that all the font representation that, wait a minute, we got half of a surrogate pair. That's wrong. But let's now create a database called check 100 CSASSC. And if you wonder why check, well, because it's shorter than that one general 100. That's all the reason. And then we're going to look at these again. And now we got 6 characters and substring returns correctly the first 3 characters, A, B, and well, gamma, so to speak. Let's look at one more thing here. I'm going to declare a table variable and the word is envarchar 10. I'm going to try to put in my word here. Well, it's 6 characters, so it should fit in, shouldn't it? But I get string abundant data will be truncated in table, column, word, and truncated value is, well, the 5 Gothic characters, but the Gothic did not fit. Because although it says envarchar 10, that is not 10 characters. That is 10 byte pairs. And that is what the Gothic people have had to put up with since SQL 2012. Or they would have had to put up with if they had still existed. Now let's move over to UTF-8. And these collations were introduced in SQL 2019. And you can easily recognize them by the fact that the suffix is UTF-8. And what they did was they took all the SC collations and tacked on UTF-8. So there is no version 80 collations for UTF-8. In the UTF-8 collations, the code pitch of varchar is always 65,001 UTF-8, so it does not follow from the collation family. One thing you should be aware of is that these collations do not support the text and in-text data types. As a matter of fact, this is true for all surrogate-aware collations. And there's one single binary UTF-8 collations, Latin 1 General 100 bin 2 UTF-8. I think they forgot to add a Turkish one. So one reason UTF-8 is popular is because it's perceived that you can save space with UTF-8. Let's have a look at this. So in UTF-8, the range from 0 to 127 takes up 1 single byte. So that's ASCII. This means that if you have an ASCII file, it's also a UTF-8 file, if it's just pure, simple ASCII file. And it also means that compared to UTF-16, well, for English, you save up to 50% space. Then we have the range from 128 to 2047. That takes up 2 bytes. So that's all other Latin characters that are not fit into ASCII. So that means for English and Polish, we may not save 50% space compared to UTF-16, but maybe 40 to 45% space. Then we have all other scripts in the European area, so to speak, Cyrillic, Greek, Arabic, and a few more ones. And well, you will still save some space for UTF-8 with these scripts because although most of the Cyrillic characters, well, they take up 2 bytes, but then they always have some punctuation, some digits, and typically also some Latin words thrown in. So they might save 5 to 10% space. But then we have the range from 2048 to 65,535. You need 3 bytes, so these are the language of India, Chinese, Japanese, Thai, So you can remember, you can guess that in East Asia, now UTF-8 is probably not that big hit. You need 50% more space. And finally, we have the range beyond the base plane. You need 4 bytes to code every character, but that is the same as UTF-16. So let's have a look at this. I'm going to start with a database called Finnish Swedish 100 CSASSC. So it's surrogate aware, but it's not UTF-8 compatible. And I'm going to look at some words again, both in nvarchar and in varchar. These are the first 3 we looked at before. So here we got surrogate characters. Here, well, we have parith in full width, and now we get it's being replaced by parith in half width. That makes reasonable. And this Gothic word became, well, for some reason, I get 12 question marks. I should only get 6. But as you see, I can only use the characters in code with 1252. Now, I'm going to create a UTF-8 database, Finnish Swedish 100 CSASSC UTF-8. And I'm going to look at these strings again. And lo and behold, I get back them all. Well, of course, it's difficult to see that this is full width and this font, but nevertheless. And this, you can see the Gothic characters, and you can see Nakameguro in kanji. Now let's look at this a little more. We're going to create a table called words and insert them, and I'm going to look at the, again, look at the length of words in characters, in the bytes, and also run a substring on them. See the first 3. And English, well, 7 characters, 7 bytes, and the first 3 are eng. Räksmånus, 10 characters, 13 bytes, because there are 3 letters that are not in ASCII. But I get back the first 3 is räk, although that's 4 bytes. Swanse, 6 characters, 8 bytes, and swa. Still, again, that's 6 bytes. Nakameguro, 3 characters. Now it's 9 bytes because it's UTF-8. And Paris, in full width, it's also 50 bytes because the full width characters are also way back in the East Asian range over there. And the Gothic string is, well, still 24 bytes like it was with the UTF-16, but it's still the first 3 characters is coming back correctly. Now, let's try this. Varchar 6, I've got a column called sun, and it's a Varchar 6 column. And I'm going to try to put in the word Swanse, which is 6 characters. So is this going to work out? Well, if you have been paying attention, you know as this is going to end. Yes, in tiers. String of binary data will be truncated in table, column sun, truncated value, swan. Because 6 characters means 6 bytes. Now, people in, let's say, well, Sweden, Poland, France, who never worked with Japanese or Gothic, never seen this before until they come to these UTF-8 collations, completely freaks out and says, what? This must be bug. What was Microsoft thinking? Well, it's completely crazy. But yes, this is just the way things are. It's 6 bytes. And as I said, the Japanese people, they have had to put up with this since SQL 2000. I think the answer standard permits to saying Varchar 6 could be 6 characters, and then you can also have an option to which you want to do. And maybe Microsoft is going to change that in the future, but I think that would be quite a bit of an architectural change. So I'm not holding my breath. So yes, Varchar 30. Means 30 bytes. So this means if you want to permit for 30 characters, well, you may go for Varchar 60. And you would still have to take the chances that you don't need to store Chinese or emojis. If you really want to be sure, you need Varchar 120. Then again, keep this in mind, a 10-byte value in the Varchar 60 does not take up more space than in the Varchar 30. But it's just that it looks odd. And it can give you some shivers, because what if someone actually adds 60 characters to this one? And we're going to print this on a form, which could give us trouble. Finally, one thing I like to discuss is if we're going to design a new application and we want to add international support. And of course, if you design a new application, you should always think international to be future-proof. Anything else is just silly, if you excuse me. So my take on this is I would go for nvarchar. The reason for this, first of all, it's more predictable. If I have nvarchar 30, that means 30 characters. Yes, because I can expect that people are not going to enter names in Gothic, and for a name column, I will not accept emojis. So I will know that that will be 30 characters. For a free text field, I might have to accept Gothic. Sorry, maybe not Gothic, but at least emojis. But yeah, then it's maybe not a big deal if I say nvarchar 2000. Yes, sure. Sorry, you put an emoji, so you only have space for 198 characters. I can live with that. Also, I get better performance. Not a big deal, but and you will see that towards the end. And when it comes to saving space, you can do that with row compression. I took a table with and put it both in UTF-8 and UTF-16 without compression, no difference in size, and it had data in beyond the ASCII set. But this is absolutely a matter of preference. I'm not saying if you think that UTF-8 is better, for example, because you think you're going to be talk with other systems that use UTF-8. Yeah, you may want to do it, but it doesn't really matter because that will still be converted on the wire. Then again, if you have an existing application that was built with Varchar without no thinking about being international, and you now have to be international, for example, let's say you're in France and your boss tells you that, oh, we have acquired a company in Poland, and I'm told that they use a different code page. Well, then having to change Varchar to NVarchar can be quite a bit of a pain. Moving to UTF-8 collations is probably less painful. You still have all the tables. You might have to consider character length, so it still can be quite a bit of work, but it's probably a slightly smoother path than having out to NVarchar. Now let's move to one of maybe the biggest pain point with collations in SQL Server, because due to legacy, collations also control metadata. And this is because you might remember way back in SQL 7, SQL Server only supported one single collation or sort order. So that also affected the system table and how they were sorted. And table names, etc., are stored in tables. So yes, they have to do it that way. Anyway, the way it works today is this: you have a server collation, and that controls the name of the server level objects, so database logins, etc. The server level collation also defines, sets up the names for temp tables and column names in temp tables and table variables. Well, that is because they live in temp2b, and temp2b is a system databases that uses the system collation. And the server collation also controls the names of variables, whereas the values of the variables follow the database collation. And the database collation, in its turn, that controls the names of the database level objects, that is tables, columns, users, etc. Although there's one exception, that is service broker objects, they always have a binary collation because or interoperability reasons, because else it would be a big deal. So it has to work across servers and multiple systems. I have a demo down here, but it's not that thrilling, and I'm a little late in my schedule, so I'm going to skip this one, but it's not that extremely exciting. I'm just going to summarize some tips for writing international software. So what you should do, I think, is you should use if you're writing a software that's going to be used in many countries, you should develop with a case-sensitive collation, both on server level and database level, or else just forget about the Turkish market, because else you will have tables being that you first created them with an uppercase I, then you refer to the lowercase I and trying to sort out that mess. No. And also, and the corollary of this is to only use lowercase for your identifiers, because else you would have if you remember, oh, did we call this one mixed case, both capital M and C, or which way did we do it? So if you use everything lowercase, I know this, I could work in with the case-sensitive collation developers for many years, and we use lowercase for identifiers. Also, avoid very short names like #v or @w. I've occasionally seen posts from people, and they were not Swedish, who being burnt by a collation like Finnish-Swedish CIAI, where they had two variables, @v and @w, and all of a sudden they clashed. And I mean, whether it should be case insensitive or case sensitive, that's a matter of preference. Some languages like Pascal, BASIC, they do case insensitive. Other languages, Perl, Python, they are case sensitive. What is a complete mess in SQL Server is that it's depending on the setting. That's just ugly. I think they should fix this by providing an option of having a fixed collation. Now, here is another pain point with collations, although this one is a more natural one. So if you have two columns that meets an expression, well, you will get a conflict. And the way to resolve this, I think we better look at this demo. So again, I'm going to move to my database, Latin 1 General, CIAS. And I'm going to move to my places database, and I'm going to add some places to it: New York, London, Paris, Munich, and Buenos Aires. And I'm also going to create a temp table, and I'm going to put London there and also Paris in all uppercase. And now I'm going to run this join. I want to find the places in my places table that also are in my places table, in my temp table. Now, you might remember that my server collation is not this one. It's a Finnish-Swedish case-sensitive one. So which collations should SQL Server use here? I mean, the comparison rules are not the same. For these particular words, that will not be an issue, but let's say that there are, well, some that would actually would be different rules for Swedish, for these two, for example, well, yeah, there is a difference, because we have one is case sensitive, one is case insensitive. So is SQL Server going to toss a coin, or no? SQL Server just raises the white flag and says, Cannot resolve the collation conflict between Latin 1 general CIAS and finish with 100 CSAS in the equal to operation. Of course, when you get this, particularly not prepared for this, it's kind of a pain. The way to resolve this is to force the collation on one side, and typically you do that on the temp table because you probably want to work with the data you have in your table. So you're going to say tplace collate Latin 1 general CIAS. And now I get back my data. Now, you might not be comfortable with hard coding the collation because, well, okay, this is Latin 1 general, but tomorrow this collation is going to run in the Czech Republic. So we're going to have a Czech collation. Well, there is a way out. We can say collate database default, which means, well, the database default for the current database, not temp to be. So then it will always be the default collation for that database, and I get it back. That works, of course, does not work, of course, if this one has a different collation from the database collation. But in many systems, you will get for one collation all over the database. It's only if you have special needs that you vary the collation. Now, what do you think about this one? This one, I'm forcing the collation on the place column from my places table to be a French case-sensitive collation. So you might think here now, the SQL Server is now going to say, I don't know which route it's going to use. I'm going to say this is a conflict. Because the reason you get this conflict error is that SQL Server doesn't want to make the choice. It just simply tells us you need to resolve this because I don't know. But it turns out this one runs, but only get back London. This is because when you force the collation on one side, this actually forces the collation on the entire expression. So you force the collation on the temp table as well. And it was a case-sensitive collation, so now I only got back London, not Paris. Now, what if I compare with a variable? So here I got at the place with Paris in all lowercase. I'm going to try to compare it both with the places table and the temp table. Will I get an error message? No, I don't. I get back Paris. Here I don't get back Paris. When you have a variable or a literal or a constant, the column will always win, and the variable and the literal will be cursed to the collation of the column. And finally, before I leave this demo, I'd like to show you the proper way of defining the temp tables. You should, rather than casting it in the expression, it's better to do this, saying place collate database default, and you will get the default collation of the current database. And it works as long as you have the same collation all over the database. And now when I run this, I don't get this error. And here's a second tip. If you actually want to make sure that you do this, make sure that you have a different server collation and database collation so you don't forget. Then again, if you expect that this database will only be alone on the server, so we will always have the same collation everywhere, then you can forget about it. But if you think that maybe we might move this database elsewhere, this can be a good habit to always have this in place. Because if you don't have to add this afterwards, it's a lot more pain than you have to do it directly. So just to summarize, so if you have a collation conflict, you need to do that by adding the collate keyword to force one of the columns to the common collation you want to do, and this casts the collation for both columns. One thing to be aware of, if you cast the collation of a column, that will kill in the index on the column, because the index is organized according to the collation you have specified. So if you cast a different collation, that index is now useless. And best practice, when you define temp tables, use collate database default for string columns to avoid the collation conflicts later on. Because you might not have them today, you might get them today with the database on a different server. And when it comes to columns, they always win. When it comes to variables and constants, they always lose against columns. Now, here are some tricks we can do with the collations where you might not have think about using collations in the first place. So removing accents in quotes, finding words that start in all uppercase, and removing invisible characters. So I'm going to create a table here called more words, and that's both a word and an original. And I will store the same word in both the word and the original. And let's see, look at the words. And there's a Danish name, there's a Swedish word, a Polish word, a Danish name again, and some Polish, some French, some Japanese, and some German. What you might notice, though, that all of these words include letters that are not in the ASCII character set. And some people say, "Oh, we want to do this. We don't want to have any of these special characters." Special characters? Hey, look, there's nothing special about these characters, as far as I'm concerned, at least. No. Anyway, I hate this, but still people want to do this. So here's a trick you can do to get rid of all these non-ASCII characters. You cast the word to a collation for a language with a different script than Latin, for example, Greek. Then you cast that to varchar, because in the code page for Greek, there are no Latin letters beyond those in ASCII, because in the upper part, there are only Greek letters. So look what happens now, and we're going to retain the original column, and you can see, look, boom, all of them are removed. The only one that did not really work out really well is this Danish character, the A literal. It came back as a question mark rather than AE. But else, yes, you can do this. Although I'll need to add the caveat that if you also have punctuation characters and other characters, it may not always work out. But the alternatives is a whole bunch of nested replace, or maybe the translate function could work for you if you're on SQL 2017 or later. But so this is a very quick thing to do this. Anyway, while now we have this data, let's see, we want to find all the words that start with uppercase. And some people, they try to do this, just like A to Z %, because they used to do this from, let's say, Unix or text editors. But when I run this, I get back all of them because, well, the like range is also affected by the collation. The range from A to Z includes, well, all the lowercase letters because it's case insensitive. Okay, when people realize, they say, okay, I'm going to do this case sensitive instead. But the result is not that much different. I got rid of one, the lowercase a, because now the range starts at uppercase a, but go all the way down to uppercase z, but includes lowercase b, lowercase c, etc., lowercase z, but not lowercase a. Now, the way to sort this out is to use a binary collation. So we get by code point, and now, boom, all of the words that start with uppercase. If you also have your own, if we do this on the original set, we would have to add the all the extra characters to this range to include those, obviously. Here's another one that also sometimes causes some confusion. I'm going to form a string here with ABZ, the null character. This is something you normally wouldn't do, but that can happen sometimes due to processing. Maybe you get data from other platforms, etc. So there is some invisible character here. And if I look at this, so there's ABZ, a null character, and XYZ. And at first it may seem that, oh, SQL Server is only storing the first 3 characters. No, it's not. It's storing all 7. There's 7 characters. Now, the one who's misbehaving here is Management Studio. Management Studio is written in C#, and all C-based languages, they think that, hey, a null byte, that's a string terminator. So Management Studio refuses to show the rest of the string. Now, we want to get rid of this sucker. So we try to do replace, count 0 with nothing at all. But much to our disappointment, it didn't help. This is, again, because car 0 in Unicode is not a defined code point. So replace says, I don't know the rules for this character. I'm giving up. I do nothing. And again, the way to resolve this is to use a binary collation. And now I get rid of that invisible character and I see all 6.
Could you replace ncar0?
Oh, let's see. That should be the same. After all, it's a Windows collation, so everything here is being conducted is being performed in UTF 16. In an SQL collation, though,
right? Yeah.
In an SQL collation, though, you would not have this problem for varchar because it's a completely different rule set, and it has a rule for car 0. So this is just a summary of what I've talked about, so I'm not going to repeat. Because I'm quite a bit short on time.
You have 23 minutes.
Yeah, well, that should be enough for the performance stuff. So, collations and performance. How does collations affect performance? Well, in most cases, a little bit, but not maybe too much. But there are 2 situations where, though, collations has a big impact on performance, and we're going to look at these. So, 23 minutes, but that includes, I figured we should have some break as well. I want to give space for that. So my aim is to stay within 75 minutes. So anyway, I'm going to have a table here called, this time I'm going to be in temp to be. And I got a table here called widths that I'm going to run the create statement and also populate it while I'm talking about it, because it takes a little bit of a minute. So anyway, this table called widths, and there's a Windows envvarchar column, which has an envvarchar 200 column, and it has a collation of lat1 general CIAS. And then there's an SQL envvarchar column, which has also envvarchar 2000, and it has the collation SQL lat1 general SQL CIS. And then there's 2 varchar columns with the same pair of collations. And all of these are labeled as unique, so there is an index of all of these columns. And then I'm just filling this up with, well, quits. So each of them will be a string of, I think, 147 characters. And there's 1,000 rows. Now, what I'm going to do here is I'm going to do a kind of a point lookup. It's not an equal, it's a like operation without a leading percent. So it's going to find a few characters. But this is a very quick operation. So what I'm going to do is I'm going to loop for 500 milliseconds to see how many iterations did I do. And the first one I'm going to do this for the Windows envvarchar column. And this takes 8,000 milliseconds. Let's now do this for the SQL column. Oh, sorry, not 8,000 milliseconds. I was able to do 8,005 iterations. That's a little lower, but maybe my laptop is busy by Zoom. This one was actually faster. Usually they are the same, but it was a little faster this time. but they usually should be about the same. Now, when I go to the Windows varchar column, let's see, I only do half, 4,103. So why is this? Well, so remember this, I have a varchar value and I compare it to an nvarchar value. By the type rules in SQL Server, the varchar column will be converted to nvarchar. That usually does not mean good for indexes. However, because all operations in varchar are actually conducted in UTF-16, the index is still usable. So SQL Server is still seeking the index, but it has to add a few extra operators to the plan. So that's why we get a speed reduction. So it's cost, usually I measure this to a factor of 2, sometimes up to a factor of 5, which may sound like a lot, but hey, these are quick operations. So depending on your workload, you may not even notice for Windows collation. But now we're going to do this for an SQL collation. And remember, in SQL collation, I completely different rules in varchar. So I was able to do only 15. So here there was a big performance impact. And here we can't talk of a factor of 2 to 5 because the index is dead. The index can't be used. It has to be a scan. So now it only depends on the size of the table or the penalty is. It could be a factor of 100. It could be a factor of 1,000. It could be a factor of 1,000,000. It could be even more. So this can be a real disaster. Of course, this is a kind of a programming error. You shouldn't do this, but this can easily happen if you, as a DBA, decide, no, use varchar because I don't want international stuff. I don't want that. Or I'm going to use UTF-8. But the developers decided to use an ORM, for example, which is basically everything modern program is based on. We're going to use Unicode, so they have Unicode, and you get this clash. Then you can, because no one thought about this, so it can quite easily happen. And with if you use a Windows collation, the damage is limited. But the SQL collation will get the revenge. Now we're going to look at doing this. We're going to do a search now with the varchar column, but now with leading percent. So in this case, the index cannot be used at all. It cannot be seeked. We can scan it, of course, but it has to go through every columns. And we're going to do this for the Windows, all of these 4 columns. And we're going to do this for all 4 at once. Oops, if I'm only able to do my selection correctly, we should do this. And of course, let's see how, well, this one took 2.5 minutes. This one also 2.5 minutes. This one, and this one was a lot faster. But these 3 were about this all the same. And this was a lot faster. Why? Well, when you do this kind of search, SQL Server does not only have to scan the table, it also has to scan the strings from start to end, more or less. It has to go, well, at least, well, not the last 2 characters, but the rest. So it has to look up and compare every character. Now, for the Unicode and UTF-16, there are very complex tables because there are very many things it has to consider, things I haven't shown you, like combining accents, etc. So it has to consider those. So, and that starts to add up. But as the SQL collation, on the other hand, it only has to think about the 255 characters that are in that collation. Yes, there are no SQL collations for Japanese. So all SQL collations are for varchar, 255 characters. So it's a lot easier, a lot smaller rules. So that's why it's so much faster. Now, so is that the lesson that we should use for these kind of searches in SQL collation with varchar? Not really, because maybe we need nvarchar because, well, we won't need to support multiple languages. Well, we can do this with a binary collation. So I can say Windows nvarchar, collate, lat1 general, bin 2. And let's see how this goes. You might remember that we had around here, slightly below 300 milliseconds for this calculation. Wow, half the speed. Although, yeah, there is a problem, 0, because this is now case sensitive and my search string is lowercase, but all these grids, the character representation are all uppercase. But there is an easy fix. I can do an upper on my varchar column and on my search string. Normally you shouldn't do this because that kills the index, but it doesn't matter here because the index is already dead because of the operation. Now, well, it was not as fast as previously, but I get back the correct count. So this is a kind of a trick to get these searches faster. You will not get exactly the same result as with the true case-sensitive collations. There are some corner cases, but you might very well get away with them. But if your users also say that they want accent insensitive searches, well, then you will probably have to go with a normal like. So these 2 slides just summarize what I've talked about in the demo, so I'm just going to not repeat that. There's actually one more case that I was reminded of just before I got a mail, but that's a bug that has been fixed with CU7, where before that there was some nasty case where you could get a problem with the UTF-8 collations, but that's a bug that have been fixed. Anyway, what I also did was I actually ran a test for all 5,508 collations. That kept my laptop busy for 9 days. I tested 5 different operations, both for varchar and varchar, to see what the result might be. And I did this in SQL 2019. And just because I'm crazy, I did this all way back in 2008 on SQL 2008. And I'm going to show you some of that data. I mean, the most, and as I point out here in the note, I mean, the effect on the real world workload is likely to be far less than the number indicates, because in the real world, well, you have scans, you have numeric comparisons, all sorts of stuff. So this is just looking at this specific operations. So here are some data. The first thing you might think, case sensitive, that should be faster than case insensitive. Turns out that not a big difference, but case insensitive, access insensitive is slightly faster. Don't know why, but maybe because this is more common, so they optimized the tables for these operations. I found out that the version 100 collations, they can be up to 30% slower than the version 80 collations. And that has to do with, I guess, because the character tables are larger, there are more characters to consider. For Windows collations, it can, actually for varchar, it can be up to 90% slower than nvarchar. That was particularly with sorting operations. Other operations, there were hardly any noticeable difference at all. And that is because of that conversion to UTF-16 and back. But that does not take in consideration that you might save space with a varchar, and saving space often means saving execution time because you make the scans smaller. For SQL collations, varchar is always faster because you have simple rules, but the difference is not always that extreme as we'd like. And yes, there are differences depending on the language or the collation family. The particularly slowest ones, I think, were Vietnamese and Hungarian, simply because they have more complex rules. But hey, if you are in Hungary, you're not going to pick a Slovak or Romanian collation just because it's faster, because your users want to get Hungarian rules, so you have no choice. And also, finally, figured it's interesting to look at UTF-8. So I figured, as long as I don't need the extra characters for version 100, and as long as you're in Europe, you can get away with the version 80 collations. If you also need support language in India, for example, then you will need a version 100 collation, or a version 90 at least. But anyway, so I figured I'm going to compare UTF-8 with varchar and an nvarchar collation with version 80. And look here, it's slower. And for the difference operation that I tried, for Are the Bytes, even twice the speed. So it comes with a cost, and which is even bigger than the normal extra overhead you get for varchar. But again, take this with a grain of salt. It does not take into account for the space reduction you might get with UTF-8, so don't put too much into this. Before I close this, I got this with the speaker deck. I like this slide a lot. Thank you for organizers, the moderators, and attendees for being here. And it's a really nice picture that they put in. Just as my final slide, just to get some references. My name is Erland Sommarskog. My email address is here again. If you have any questions I don't answer right now, please feel free to drop me a line at any point. You have slides and scripts on my website, sommarskog.se/present. And if you do the demos, here's a cleanup script that will just drop all the databases with collation names. So that was I had to say today. And are any questions somewhere?
I'm just amazed, and we were a couple of us were joking in the beginning, like you have a high performance mode on, and will you make it in time? But you did. No, I think we're all just gobsmacked. What was there? There was something about smörgåstårta, something about no lock and poop emojis. Hugo says, I still want a set option to make Collate database default, the default for all temporary objects. I agree with him. That's a great idea.
Yeah, could be useful, yes. But I think it's even better though is to have simply that means the data collection that does not address that. That would be help. But then again, if you sort of mix collation in the database, and sometimes you have to do that because you might generally do things case insensitive, but you might business rules that say this one has to be case sensitive. And actually, I have the idea that if you have things like codes, like currency code, for example, that should be a binary collation, because why would you ever want to have that in anything else? First of all, it's faster, and why would you have to sometimes see sec as uppercase and sometimes lowercase, etc. Yeah.
Yeah, totally. I tend to install the developments where I have a different server collation compared to the database collation. because inevitably you will run into stuff where you create temp table objects and then you sort of, you get something in a stored procedure somewhere wrong, and that collation error wouldn't show in your dev development if you didn't. It would show up at the client, and at which point it's harder to fix.
Yeah, that's also so. As I said, I've been working.
I would even set it to case sensitive actually, but that's just me being terrible on my colleagues.
Yeah, so I work with a developer with a product. It was not for really international market, but we use the case sensitive collation exactly because, and this was a decision making already in the 6.5 time. So you do so if the server says that we go by case, if the client says if we go by case sensitive, well, we have developed case insensitive, you're kind of host. So that's why we made the decision to always use case sensitive. And once you get used to it, well, I can't say why I ever download queries from the forums, and people have mixed case of what's the point of sometimes spelling the customer with a capital C and sometimes in lowercase c and sometimes all uppercase. I mean, I don't see the point.
It's just sloppy, right? But if you use Linux or Unix for any length of time, or code in C for that matter, you get used to the case sensitive thing. Or you actually just make a general rule to have everything in lowercase, which I have opinions on, but okay. Nagia says, wow, this was incredible. You went at 3x speed, but this has been a great eye-opener. My notepad is full and my mind is at capacity. I think I'll have to lie down. Thank you, Erland.
Yeah.
Martin agrees. So many great details. Thanks a lot, Erland.
Yeah, it was a bit cramped, but well, I'm usually not known for going particularly slow in my presentations, but yeah.
I think it was an eye-opener, really. I had no idea that sort of collations could take up more than, say, 15, 20 minutes. I don't know. I stand corrected.
Yeah, that's more things I could have shown you, for example, that could confuse people, for example, combining accents they have in Unicode. But you don't come across these very often. Although I actually had someone on the forums who actually had a problem with combining accents. But they're not very commonly used. But when they decide Unicode, the reason they want to have these combining accents was, well, to reduce the number of code points. I remember I was on a mailing list that was because there was two initiatives, Unicode and ISO 10646, and 10646 was aiming at a 32-bit standard, and Unicode tried to make it a 60-bit, and the end result was kind of a compromise. But at least there was only one standard. It was not way back in the 80s when about every vendor had their own 8-bit character set, and it was a complete mess.
Yikes. Yeah. So what say we take an 8-minute bio break? Over in the DBA channel, Mikey Bronowski is up in a couple of minutes.